Consciousness is one of the greatest mysteries of existence, raising the profound question of how awareness arises from physical matter. Scientists can map brain activity, track neural signals, and measure chemical reactions, yet none of this explains experience itself, the vivid sense of being aware, of thinking and feeling. This enigma has led some researchers to look beyond traditional biology toward the strange and mind-bending world of quantum physics. Could the same laws that govern subatomic particles also shape our thoughts and perceptions? The possibility that consciousness is not merely produced by the brain, but interwoven with the fabric of the universe, challenges the very boundaries between mind, matter, and reality itself. If you want to uncover how your mind might be connected to the cosmos, watch this video till the end and subscribe to the channel. Let's begin. When we speak of consciousness, we are referring to that inner light of awareness that allows us to experience the world, to see, to think, to feel, and to know that we exist. Scientists describe it as the state of being aware of one's surroundings and internal experiences. The constant stream of perceptions, sensations, memories, and thoughts that together create our sense of self. Yet, despite being the most immediate and intimate aspect of our existence, consciousness remains nearly impossible to define in purely scientific terms. Unlike heartbeats or brainwaves, awareness cannot be weighed, measured, or directly observed. Neuroscientists can identify the brain regions active when we make decisions or feel emotions, but they cannot point to a single structure and say, "Here lies consciousness." The challenge lies in its subjectivity. Every scientific method depends on objective measurement, but consciousness is, by nature, a first-person experience. No external instrument can fully capture what it feels like to taste sweetness, to dream, or to fall in love. This subjective quality makes consciousness a unique problem in science, one that blurs the line between physics, biology, and philosophy. Some thinkers argue that this elusiveness might be a clue. Perhaps consciousness doesn't arise solely from physical processes at all, but instead reflects something deeper and more fundamental about the nature of reality. And to explore that possibility, we must look toward the realm of the very small, the strange, invisible world of quantum mechanics. Quantum mechanics is the branch of physics that reveals how reality behaves at its most fundamental level, the realm of atoms and subatomic particles. Unlike the predictable world we see every day, where a ball rolls in one direction and a planet orbits in another, the quantum world is astonishingly strange. Here, particles can act like waves, existing in multiple places or states at once, a phenomenon known as superposition. Imagine flipping a coin, but instead of landing on heads or tails, it remains in a blend of both until someone observes it. Only when it's measured or looked at does it settle into one outcome. Even more mysterious is entanglement, the quantum connection that links particles across vast distances. When two particles become entangled, a change in one instantly affects the other, no matter how far apart they are, even across galaxies. Einstein famously called this spooky action at a distance because it seemed to defy the limits of space and time. These principles, superposition, wave-particle duality, and entanglement, form the foundation of quantum mechanics and show that reality at its smallest scales does not follow the rigid logic of classical physics. What's most intriguing is how this microscopic world might relate to our macroscopic experience, the world of thought, perception, and consciousness. If the brain operates not only as a biological machine, but also as a quantum system, then the mysteries of awareness might be deeply tied to the very same principles that govern the behavior of subatomic particles. Could our minds, like those quantum particles, exist in multiple states of possibility, collapsing into awareness only when observed by the self? The connection between the quantum world and the mind is one of the most fascinating and controversial ideas in modern science. A bridge between two of humanity's deepest mysteries, the nature of consciousness and the nature of reality itself. While neuroscience has made remarkable progress in mapping brain activity and understanding neural communication, it still cannot explain why electrical signals and chemical reactions create subjective experience, the inner awareness we call consciousness. This explanatory gap has led some scientists and philosophers to suggest that the key might lie not in classical biology, but in the subtle and counterintuitive domain of quantum mechanics. In classical physics, the brain is viewed as a kind of biological computer, an intricate network of neurons exchanging signals, generating thoughts and emotions through deterministic chemical and electrical processes. This view assumes that every mental event can be traced back to a physical cause, leaving little room for mystery or free will. Yet, the more we study consciousness, the less it seems to fit neatly into this model. Awareness is not merely computation, it's subjective experience, a quality that doesn't appear to emerge from the firing of neurons alone. This realization opens a window to something deeper. Perhaps consciousness is not a byproduct of brain activity, but a manifestation of quantum processes occurring within it. The idea that quantum effects might play a role in the mind has been explored by some of the most daring scientific thinkers of our time. They argue that the strange principles governing quantum particles, such as superposition and entanglement, might also operate within the complex, delicate structures of the brain. If so, our thoughts could exist, at least momentarily, in multiple states at once, before collapsing into a single conscious experience. In this view, consciousness arises not from deterministic chains of cause and effect, but from a probabilistic field of possibilities. A living, dynamic quantum system that constantly resolves itself into awareness. This concept also touches upon the observer effect in quantum physics, the phenomenon where the act of observation changes the state of what is being observed. In quantum experiments, particles exist in multiple potential states until they are measured, at which point the wave of possibilities collapses into one outcome. Some theorists have suggested that consciousness might be more than a passive observer of this process. It might actually be the collapse itself. In other words, the very act of being aware could be the moment when quantum possibilities crystallize into physical reality. Consciousness and the universe would then be inextricably linked, each giving rise to the other in an ongoing dance of observation and creation. This perspective challenges traditional neuroscience, which tends to view consciousness as a localized phenomenon confined to the brain's neural circuits. Quantum-minded thinkers propose instead that consciousness might be non-local, not bound by the limits of space, time, or individual identity. Just as entangled particles influence each other instantly across vast distances, perhaps the mind too operates in a field of interconnected awareness that transcends the boundaries of the body. This would mean that the brain functions not as the source of consciousness, but as a receiver or filter for it, tuning into the universal field much like a radio tunes into specific frequencies. There are several reasons why this idea has gained traction. First, quantum physics has already shown that the fabric of reality is far more mysterious and interconnected than once imagined. Space and time themselves appear to emerge from underlying quantum relationships, and particles can influence each other instantly without any apparent transfer of energy or information. If the entire universe is built upon this quantum foundation, it would not be far-fetched to imagine that consciousness, one of the universe's most complex and mysterious phenomena, might also be rooted in it. Second, there are hints of quantum behavior within biological systems that challenge the long-held assumption that quantum effects are too fragile to survive in warm, wet environments like the brain. For example, Studies in quantum biology have shown that quantum coherence may play a role in photosynthesis, helping plants convert sunlight into energy with near-perfect efficiency. Similarly, the magnetic navigation of certain birds appears to depend on quantum entanglement within their eyes. These discoveries suggest that life, at its deepest level, might have evolved to harness quantum effects. And if that's true for cells and plants, why not for neurons and consciousness? However, the leap from quantum biology to quantum consciousness remains a daring one. Critics point out that the brain is too noisy and thermally chaotic to maintain quantum coherence for long enough to influence mental processes. Yet, proponents argue that the brain's microstructures, especially microtubules within neurons, might provide a protected environment where quantum information could persist. These microtubules, tiny cylindrical structures that form part of the cell's cytoskeleton, are thought by some researchers to function as quantum processors, enabling computations far more powerful and subtle than classical neurons could achieve alone. If the mind indeed operates on quantum principles, it could explain many aspects of human experience that have puzzled scientists for decades: intuition, creativity, synchronicity, and even free will. In a deterministic, classical universe, every decision we make would be nothing more than the inevitable result of prior causes. But in a quantum universe, probabilities, potentials, and uncertainties open the door to choice, to agency. The conscious mind could act as the organizing principle that collapses these probabilities into meaningful outcomes. Ultimately, bridging science and mind through quantum theory invites us to rethink not only what consciousness is, but what reality itself might be. If awareness and the physical universe are intertwined at the quantum level, then our thoughts, perceptions, and intentions may be far more powerful than we realize, subtly shaping the world we experience. This doesn't mean that consciousness can defy physics. Rather, it suggests that consciousness is part of physics, an intrinsic aspect of the quantum fabric of reality. This vision of mind and matter as two sides of the same cosmic coin is both humbling and exhilarating. It implies that every act of awareness, every moment of perception, is a quantum event, a meeting point between the infinite potential of the universe and the intimate focus of human experience. And as we continue exploring this frontier, the next great question emerges naturally. If consciousness arises from such profound depths of reality, what exactly makes it so difficult to understand? This is the essence of what philosopher David Chalmers famously called the hard problem of consciousness. The hard problem of consciousness, a term coined by Australian philosopher David Chalmers in the 1990s, sits at the very core of humanity's struggle to understand the mind. Unlike the easy problems of neuroscience, which deal with how the brain processes information, recognizes patterns, or controls movement, the hard problem asks a question that science to this day cannot answer. How and why does physical brain activity give rise to subjective experience? When neurons fire and electrical signals flow across synapses, we can trace those processes with astonishing precision. We can even map which parts of the brain activate when someone tastes chocolate, feels fear, or recalls a memory. But no amount of data, no matter how detailed, explains what it feels like to experience those sensations. The firing of neurons doesn't inherently produce the sensation of sweetness, the color red, or the emotion of love. Those feelings, known as qualia, belong to the private, first-person realm of experience, a dimension that remains invisible to external measurement. This is the crux of Chalmers' argument. Science, built upon objective observation, struggles to explain something that is fundamentally subjective. We can describe how information is processed in the brain, but not why it feels like something to process it. Why does the firing of certain neurons correspond with the vividness of color, the warmth of nostalgia, or the pain of heartbreak? Why is there a self, a conscious witness, behind the brain's biochemical machinery? These questions are so profound that some philosophers call them the last great mystery of science. Chalmers proposed that consciousness may not be something that can be derived from physical processes at all. Instead, it may be a fundamental property of the universe, just like space, time, and energy. In other words, awareness might be woven into the fabric of reality itself. This idea, while radical, opens the door for quantum theories of mind. If consciousness is fundamental, then perhaps it doesn't emerge from matter. Perhaps matter itself is a manifestation of consciousness on a deeper level. This is where the quantum perspective enters the discussion. Quantum physics has revealed that the physical world is not made of solid objects, but of probability waves, existing in superposition until observed. That means the universe at its deepest level doesn't behave like a machine, but like a field of possibilities. And consciousness, by observing and collapsing these probabilities, might play a role in turning potential reality into actual experience. The hard problem, then, might not just be about how the brain generates awareness, but how awareness participates in the generation of reality itself. From this perspective, the brain is no longer seen as merely a biological engine producing consciousness, but rather as an interface, a receiver or a resonator, through which consciousness interacts with the physical world. This concept aligns beautifully with quantum theories, suggesting that observation is fundamental to existence. If consciousness influences or even creates reality by collapsing quantum wave functions, then the boundary between mind and matter dissolves. Consciousness would not be an afterthought of evolution, but an intrinsic ingredient of the cosmos. Chalmers' framing of the hard problem forces science to confront an uncomfortable truth. Even the most advanced neuroimaging technology cannot capture the essence of what it means to be aware. We can scan the brain, but we cannot find the observer, that internal sense of I who experiences everything. It's as if consciousness hides in plain sight, inseparable from our existence, yet beyond the reach of instruments. This profound limitation suggests that a purely materialist approach may never be enough. That realization has encouraged scientists and philosophers to look toward quantum theory as a potential bridge between objective physics and subjective experience. Quantum mechanics, after all, already challenges our deepest assumptions about what is real. Particles exist in superposition, connected across vast distances through entanglement, and the act of observation itself alters outcomes. These features seem eerily resonant with the mysteries of consciousness, unity across separateness, the collapse of possibilities into definite awareness, and the intimate role of the observer in shaping what is real. The hard problem, in essence, is the intellectual invitation to explore consciousness not merely as a byproduct of biology, but as a key component of the universe's structure. It is the open door through which quantum consciousness theories step, suggesting that mind and matter are not separate realms, but different expressions of the same underlying quantum reality. And while Chalmers himself did not claim that quantum physics is the solution, his framing of the problem made such hypotheses not only possible, but scientifically respectable to consider. For the first time, physicists and neuroscientists found common ground in mystery itself. The realization that both consciousness and quantum reality resist reduction to simple mechanisms. This intersection gave rise to one of the most ambitious and intriguing theories ever proposed, a bridge between the microscopic universe of quantum mechanics and the macroscopic world of thought. It is here that the work of physicist Roger Penrose and anesthesiologist Stuart Hameroff emerges, proposing that the enigma of consciousness might find its answer deep within the very cells of the brain, in a theory known as orchestrated objective reduction, or Orch-OR. The collaboration between Sir Roger Penrose and Dr. Stuart Hameroff gave rise to one of the most daring and imaginative attempts to solve the riddle of consciousness: the orchestrated objective reduction theory, more commonly known as Orch-OR. This theory proposes that consciousness does not emerge from complex neural computation alone, but from quantum processes occurring deep within the brain's microarchitecture. It represents a bold synthesis of physics, biology, and philosophy, an attempt to explain subjective experience as a real, physical phenomenon grounded in the quantum structure of reality itself. Sir Roger Penrose, a world-renowned mathematical physicist and Nobel laureate, had long been fascinated by the mysteries of consciousness. He became skeptical of the idea that the mind could be fully explained by classical computation, the idea that the brain functions like a biological computer, processing inputs into outputs according to deterministic rules. In his influential 1989 book, The Emperor's New Mind, Penrose argued that human understanding, creativity, and insight go beyond what any algorithmic system could produce. He pointed to a unique gap between the capabilities of machines and the qualities of human thought, suggesting that consciousness must arise from non-computable processes, mechanisms that transcend the limits of standard computation. Penrose found a possible candidate for such non-computable behavior in the mysterious world of quantum mechanics. He proposed that certain quantum processes, specifically a form of wave function collapse he called objective reduction, OR, could form the basis of conscious experience. According to standard quantum mechanics, particles exist in a state of superposition, multiple possible states at once, until observed or measured, at which point the wave function collapses into a single reality. Penrose theorized that this collapse isn't caused by observation per se, but by an intrinsic property of space-time geometry itself. When quantum superpositions reach a threshold of instability in space-time curvature, they undergo a self-collapse, an objective physical event. And crucially, Penrose proposed that each of these collapses could correspond to a moment of consciousness, a quantum tick of awareness. However, Penrose was a physicist, not a neuroscientist. He needed a biological structure capable of supporting and orchestrating such delicate quantum processes within the warm, noisy environment of the brain. Enter Dr. Stuart Hameroff, an anesthesiologist and consciousness researcher at the University of Arizona, who had spent decades studying microtubules, tiny, cylindrical protein structures that form part of the neuron's cytoskeleton. Microtubules act like scaffolding, maintaining cell shape, assisting in transport, and even coordinating cell division. But Hameroff saw something more: an extraordinarily intricate and dynamic lattice structure that might be capable of quantum-level information processing. Together, Penrose and Hameroff developed the Orch-OR theory, orchestrated objective reduction. In this model, the microtubules inside neurons are not just structural supports, but quantum computers, capable of sustaining coherent quantum states long enough for wave function collapse, Penrose's objective reduction, to occur. These collapses are not random, but orchestrated by the brain's biology, meaning that neural activity coordinates and modulates them to produce ordered, meaningful experiences. Consciousness, therefore, arises from the orchestrated self-collapse of quantum wave functions within the microtubules, a direct fusion of physics and biology. To visualize this, imagine the brain not merely as a network of firing neurons, but as a vast symphony of quantum vibrations, where each neuron's microtubules act as instruments playing in harmony. Every time a quantum wave collapses, every objective reduction, a flicker of conscious awareness is born. These flickers occur billions of times per second, blending together to create the seamless flow of consciousness that we experience as thought, perception, and emotion. One of the most revolutionary aspects of Orch-OR is that it implies consciousness is not a mere epiphenomenon, not something the brain happens to produce as a side effect, but rather a fundamental process in nature. The brain doesn't create consciousness out of nothing. It tunes into and orchestrates it through quantum events occurring in microtubules. This interpretation aligns with the idea that consciousness is woven into the universe itself, that the brain is not a generator, but a sophisticated receiver and amplifier of an underlying field of awareness. Critics have often challenged Orch-OR, arguing that quantum coherence, the delicate state in which quantum systems maintain superposition, cannot survive in the brain's warm, wet conditions. Quantum effects are typically observed at near absolute zero temperatures, where thermal noise is minimized. Hameroff and Penrose counter this objection by pointing to evidence from quantum biology, such as the discovery that quantum coherence can indeed occur in biological systems at body temperature, in photosynthesis, bird navigation, and even olfactory sensing. They argue that microtubules are structured in such a way that they could protect and preserve quantum coherence through their ordered lattice and hydrophobic interiors, acting as miniature quantum resonators. Further, anesthesiology provides an intriguing line of indirect evidence supporting Orch-OR. Hameroff observed that most anesthetic drugs, which temporarily abolish consciousness, bind specifically to microtubule proteins called tubulins. This suggests that consciousness might indeed depend on microtubule function, and disrupting that function even slightly could switch off awareness. Such findings, while not conclusive, provide a tantalizing hint that the key to consciousness lies deeper than the synapses, buried in the subcellular quantum machinery of life itself. In Orch-OR, each conscious moment is a quantum event, a collapse of possibilities into experience. The brain, through its microtubular network, orchestrates these collapses into meaningful sequences, giving rise to perception, thought, and memory. Over time, these orchestrated collapses create the continuous narrative of our inner life, a quantum symphony resonating in harmony with the universe's fundamental fabric. This theory, while controversial, offers a poetic and potentially revolutionary perspective on what it means to be conscious. If Orch-OR is correct, consciousness is not an accident of evolution, nor a fleeting illusion produced by neurons, but an intrinsic part of the cosmic order, a self-aware ripple in the quantum sea of existence. The implications are profound. It suggests that every moment of awareness connects us directly to the universe's most fundamental processes. But to fully grasp how this theory works, we must understand the very structures at its heart, the microtubules themselves. These intricate nanoscale lattices are not just passive scaffolds, but may be the true quantum engines of consciousness, capable of bridging the divide between matter and mind. Microtubules are among the most fascinating and complex structures within living cells, and according to the Orch-OR theory, they might hold the key to understanding consciousness itself. To most biologists, microtubules are part of the cytoskeleton, the intricate internal framework that gives cells their shape, stability, and the to-move materials around. But to quantum consciousness, theorists like Roger Penrose and Stuart Hameroff, these tiny tubular structures are far more than cellular scaffolding. They are potential quantum information processors, capable of orchestrating the very patterns that give rise to awareness. At their most basic level, microtubules are cylindrical polymers composed of repeating protein subunits called tubulins. Each tubulin molecule consists of two smaller parts, alpha tubulin and beta tubulin, which pair together to form dimers. These dimers align end to end in long chains known as protofilaments, and about 13 of these protofilaments join side by side to form a hollow tube about 25 nanometers in diameter, far smaller than the wavelength of visible light, but enormous in molecular terms. These tubes extend throughout the neuron, forming highways for transporting nutrients, neurotransmitters, and molecular signals. They also play critical roles in cell division, intracellular communication, and structural integrity. However, what makes microtubules particularly intriguing in the context of consciousness is their highly ordered and dynamic architecture. The arrangement of tubulin molecules within a microtubule forms a kind of geometric lattice, often referred to as a quantum lattice, because of its striking similarity to computational grids used in quantum systems. Each tubulin dimer has regions of electric polarity, positive and negative charges that can shift states, much like binary bits in classical computers. Hameroff proposed that these charge states might also exist in quantum superposition, functioning as qubits, quantum bits, capable of holding multiple values simultaneously. In this model, microtubules become quantum processors, not just storing and transmitting information, but performing computations that depend on the probabilistic nature of quantum mechanics. Because tubulins can rapidly switch between conformational states, and because their arrangement allows for coherent resonance patterns, microtubules could, in theory, support the kind of quantum coherence necessary for Orch-OR's proposed mechanism of consciousness. But how could such delicate quantum states survive in the warm, wet, and chaotic environment of the brain? This question lies at the center of the debate surrounding quantum consciousness. Traditionally, physicists believed that quantum coherence, the ability of quantum particles to exist in multiple states simultaneously, can only be maintained at extremely low temperatures near absolute zero. In biological systems, thermal noise and molecular collisions should destroy coherence almost instantly, a process known as decoherence. Yet, Hameroff and Penrose argue that microtubules are uniquely structured to resist decoherence. The interior of a microtubule is not a chaotic soup of molecules. Rather, it is a highly organized, hydrophobic, water-repelling environment that may shield quantum states from external interference. The tubulin lattice itself forms a repeating, symmetrical pattern that could facilitate quantum coherence through collective vibrations, oscillations that allow the entire microtubule network to resonate as a unified quantum system. This means that, under the right conditions, quantum information might be stored, transferred, and processed within microtubules for significant periods, even at body temperature. Supporting this idea, research in quantum biology has already demonstrated that quantum coherence can occur in living organisms. For example, in photosynthetic bacteria, quantum effects enable energy to transfer through molecular systems with astonishing efficiency. Similarly, birds such as robins appear to use quantum entanglement in their magnetic navigation, detecting the Earth's magnetic field through entangled electron pairs in their retinas. These discoveries show that life, far from being incompatible with quantum processes, may have evolved mechanisms to harness them. Hameroff and Penrose believe the brain is doing something similar, but on a vastly more sophisticated scale. In their theory, the microtubule network inside neurons acts like a massive parallel processing system, one capable of quantum computation on a scale unmatched by any artificial system. Each neuron contains roughly 10 to the power of 9 tubulin dimers, and the brain itself contains about 10 to the power of 11 neurons. If even a fraction of these tubulins participate in coherent quantum activity, the amount of quantum information processing would be astronomical. Consciousness, then, could arise from the orchestrated interplay of these quantum events as microtubule lattices across neurons synchronize their vibrations and collapses in exquisitely coordinated patterns. Another fascinating property of microtubules is their apparent ability to communicate across distances within the cell through resonance and electromagnetic coupling. Some researchers have proposed that microtubules might even support quantum entanglement between different regions of the brain, linking neural processes in a way that classical biology cannot explain. This could account for the unity of conscious experience, how we perceive the world as a single, continuous stream rather than fragmented neural events scattered across the cortex. Furthermore, Hameroff's background in anesthesiology provides compelling circumstantial support for the microtubule hypothesis. Most general anesthetics, despite their chemical diversity, share one crucial trait. They bind preferentially to tubulin proteins within microtubules. When this binding occurs, consciousness fades, yet basic brain activity continues. This correlation suggests that the microtubules themselves may play a direct role in generating conscious experience. By disrupting quantum coherence within these structures, anesthetics may effectively turn off the quantum computations that give rise to awareness. Taken together, these insights present microtubules not as inert scaffolding, but as biological quantum processes, bridging the gap between the physical and the experiential. They offer a physical substrate for Penrose's concept of objective reduction, a place where the collapse of quantum wave functions could occur in orchestrated harmony with neural activity. Each collapse, each flicker of quantum coherence resolving into a definite state, could correspond to a moment of consciousness. In this framework, the human mind becomes a symphony of quantum events. Microtubules, acting in vast networks throughout billions of neurons, orchestrate coherent patterns of activity that collapse into conscious experience, giving rise to thought, emotion, perception, and will. The brain, in this view, is not merely a classical machine, but a quantum instrument, harmonizing with the deep rhythms of the universe. If this interpretation is true, then understanding microtubules means understanding the very mechanism through which the universe becomes self-aware. But to grasp how this process might actually produce consciousness, we must now explore the principle at the heart of Penrose's theory, the process he calls objective reduction, the very moment when quantum potentiality crystallizes into awareness. In quantum mechanics, every particle, every bit of matter and energy exists not as a definite thing, but as a wave of possibilities. This is known as the wave function, a mathematical description that tells us all the possible states a quantum system could be in at once. For example, an electron doesn't have a single position until it's measured. It exists in a cloud of potential locations. When we observe it, that cloud, that wave of probabilities, suddenly collapses into one definite reality. This mysterious event is called wave function collapse, and for decades, physicists have debated what actually causes it. Most interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that collapse happens when a measurement or observation is made, as though the universe only becomes definite when it's observed. But Penrose was deeply dissatisfied with this idea. He found it philosophically incomplete and physically unsatisfying. Why should observation, something seemingly outside the equations of physics, cause a physical event in nature? Instead, Penrose proposed that wave function collapse is an objective process, something that happens naturally without the need for a conscious observer. He called this process objective reduction, or OR. According to Penrose, superposed quantum states, for instance, a particle being in two locations at once, correspond to slightly different configurations of space-time geometry. Because of Einstein's general theory of relativity, mass and energy determine the curvature of space-time, meaning that when a quantum system exists in multiple states simultaneously, space-time itself must exist in multiple overlapping geometries. But space-time cannot sustain this duality indefinitely. The universe cannot tolerate two contradictory curvatures existing together. When the difference between these geometries, what Penrose calls the gravitational self-energy, reaches a critical threshold, the superposition spontaneously collapses into one definite state. This collapse is not random, nor is it the result of measurement. It is a self-organizing event in space-time, driven by the universe's own geometry. In other words, the universe chooses a definite outcome because it must, because the fabric of reality itself cannot hold two contradictory possibilities forever. That moment of resolution, when the wave function collapses from potentiality into actuality, is what Penrose identifies as a moment of objective reduction. Now, here's where this theory takes a profound and unexpected turn. Penrose proposed that each act of objective reduction corresponds to a unit of conscious experience, a quantum moment of awareness. In his view, consciousness is not something that merely observes the collapse. It is the collapse. Every time the universe resolves quantum uncertainty into definite reality, an event of awareness occurs. The universe, through these quantum state reductions, becomes self-aware in discrete fundamental moments. In isolation, these events would be like flickers of awareness scattered throughout the cosmos. But within the human brain, and specifically within the microtubules of neurons, as Hameroff later proposed, these quantum collapses don't happen chaotically or randomly. They occur in exquisitely orchestrated patterns, synchronized by the biological and electromagnetic rhythms of the nervous system. This orchestration gives rise to the seamless continuity of consciousness, the feeling of an unbroken stream of experience flowing through time, hence the full name of their joint theory, Orchestrated Objective Reduction, Orch-OR. Penrose believed that because objective reduction is governed by the fundamental laws of space-time and gravity, it cannot be simulated or reproduced by classical computers. This was a crucial distinction. A machine can mimic intelligence, but not awareness, because consciousness involves a direct participation in the fundamental structure of reality. In Penrose's view, this makes consciousness an intrinsic feature of the universe, not something that can be generated artificially or reduced to computation. Consciousness, therefore, might be woven into the same fabric that shapes the cosmos itself. To understand how this might translate into human experience, consider the brain as a vast orchestra of quantum players, microtubules acting as instruments whose resonances are tuned to the subtle frequencies of the quantum field. Each note corresponds to a tiny quantum event, a superposition collapsing via objective reduction. When these events are orchestrated by neural activity, the result is not noise, but a coherent symphony: perception, thought, emotion, and the flow of self-awareness. Every moment of consciousness, from the simplest sensory experience to the deepest meditation, could be seen as a cascade of orchestrated collapses, billions of quantum events resolving into the unified field of awareness we call mind. This approach provides an elegant, if speculative, answer to the hard problem of consciousness. It suggests that subjective experience arises not from classical computation, but from the universe's intrinsic tendency to resolve quantum uncertainty. Consciousness, in this view, is not an emergent property of matter, but a fundamental process through which matter interacts with space-time itself. Each act of awareness, each moment when something happens in the mind, is literally the universe choosing one version of itself to exist over all others. The implications of this are staggering. If objective reduction events underlie consciousness, then awareness is not confined to biological organisms. It is, in principle, a universal phenomenon, one that could occur anywhere quantum superpositions collapse under gravitational influence. This opens the door to a profoundly interconnected vision of reality, where consciousness is not an accident of evolution, but an integral feature of the cosmos, manifesting through systems capable of orchestrating these quantum events. In this way, the Orch-OR model redefines what it means to be conscious. It paints a picture of the mind as a bridge between the quantum and classical worlds, a meeting point where the probabilities of the quantum realm crystallize into the definite realities of experience. The human brain, through its microtubules and their orchestrated quantum collapses, becomes a kind of cosmic interface, connecting our inner awareness to the fundamental processes shaping the universe itself. And yet, even as this theory expands the boundaries of what science dares to imagine, it also provokes the next crucial question. How does this quantum brain model differ from the classical view of neuroscience that dominates modern thought? What separates a mind defined by quantum collapse from one explained purely by electrochemical signals? To answer that, we must explore the contrast between classical and quantum brain models, and what each reveals about the nature of consciousness. In traditional neuroscience, the brain is often portrayed as the most advanced biological machine in the known universe, an intricate network of approximately 86 billion neurons, each connected to thousands of others through synapses. These neurons communicate using electrical impulses and chemical messengers, forming a complex web of signaling that underlies thought, memory, emotion, and behavior. Every sensation you experience, every decision you make, and every dream you have can, in this view, be traced to patterns of electrochemical activity. When one neuron fires, it releases neurotransmitters that either excite or inhibit neighboring neurons, forming cascades of activity that ripple across neural networks. This classical model of the brain, grounded in the physics of macroscopic deterministic systems, has achieved remarkable success. It explains much of what we know about how information is processed, how reflexes work, how memories form, and how brain damage can alter cognition or personality. The classical brain operates according to cause and effect, where every mental state arises from the state that came before it. From this perspective, consciousness is thought to emerge from the collective behavior of billions of neurons, much like a melody emerges from the coordinated vibrations of many musical notes. But despite its explanatory power, this model leaves a profound gap: the subjective experience of consciousness. It describes the mechanics of the orchestra, but not the music itself. Neuronal firings and chemical exchanges are physical events, measurable and predictable. Yet none of them, by themselves, account for what it feels like to be aware. A purely classical system, no matter how complex, operates on deterministic rules that cannot, by definition, generate self-awareness or free will. This has led thinkers like Penrose and Hameroff to argue that something deeper, something fundamentally non-classical, must be at work within the brain. The quantum brain model offers a radically different perspective. Rather than viewing the mind as an emergent property of neural computation, it suggests that consciousness arises from quantum processes taking place within the brain's microstructures, particularly the microtubules. In this view, the brain isn't just a network of neurons, it's a quantum coherent system, capable of harnessing the strange and powerful principles of quantum mechanics: superposition, entanglement, and wave function collapse. In classical physics, an object exists in a single, definite state at any given time. In quantum physics, however, particles can exist in multiple possible states simultaneously, a phenomenon known as superposition. Only when they interact with their environment or are measured do they collapse into a definite state. The quantum brain model posits that microtubules within neurons can maintain such superpositions of quantum states, meaning that, for brief moments, they hold multiple possibilities of thought, perception, or action simultaneously. Conscious awareness, then, may arise when these quantum possibilities collapse into definite outcomes through Penrose's process of objective reduction. This would mean that your thoughts are not merely the result of a deterministic chain of neural events, but the product of quantum choices, probabilistic resolutions of superposed states within your brain. In other words, your mind may operate as a quantum decision engine, where consciousness itself is the act of the wave function collapsing, selecting one reality from a spectrum of possibilities. Even more mysterious is the phenomenon of quantum entanglement, in which particles become linked in such a way that the state of one instantly influences the state of another, no matter how far apart they are. If similar entanglement occurs among quantum states within or between microtubules, it could mean that different regions of the brain, or even different brains, could share instantaneous correlations beyond classical communication. This might explain the profound sense of unity and integration that defines conscious experience. You are not a collection of separate processes. You are one coherent field of awareness, a singular observer arising from countless entangled quantum events. In contrast, the classical model cannot easily explain this unity. Traditional neuroscience views consciousness as an emergent property of distributed neural activity, yet it struggles to account for how these separate processes are bound together into a single, seamless experience, a problem known as the binding problem. Quantum entanglement, however, offers a natural mechanism for this integration. Entangled quantum states inherently behave as one system, even when spatially separated. Thus, the oneness of consciousness may literally be encoded in the non-local nature of quantum information. Another crucial difference lies in causality and determinism. The classical brain operates under deterministic rules. Given the same inputs and conditions, it will always produce the same outputs. This view leaves little room for free will or genuine creativity. The brain is, at best, a biological automaton. The quantum brain model, however, introduces a realm of probabilistic freedom. Quantum events are inherently unpredictable. They are governed by probabilities, not certainties. When these quantum processes are amplified into neural activity through Orch-OR, they could provide the physical basis for free will, conscious choices that are neither predetermined nor purely random, but self-determined within the probabilistic framework of quantum mechanics. Moreover, the observer effect in quantum theory, the principle that observation affects reality, finds an intriguing parallel in consciousness itself. In the quantum brain model, awareness isn't a passive observation of pre-existing neural states. It is an active participation in their collapse. The conscious observer within us, therefore, might not merely witness reality, but help shape it through the continual process of wave function reduction. This notion blurs the boundary between mind and matter, suggesting that they are two sides of the same coin, that consciousness may be both the product and the participant in the unfolding of physical reality. One might visualize it this way. The classical brain is like a high-speed digital computer, processing information through logical operations and firing sequences. The quantum brain, on the other hand, is more like a symphony of probability waves, fluid, interconnected, and holistic. Classical computation follows linear cause and effect. Quantum computation allows leaps, intuition, and creativity, drawing from a vast field of potential outcomes. Consciousness, then, could be seen as the harmony that emerges when the quantum orchestra collapses its notes into the song of awareness. Critically, these two models need not be entirely opposed. In fact, the quantum brain hypothesis suggests that the brain operates on two levels simultaneously. 1. A classical level, responsible for stable neural processing, memory storage, and sensory coordination. 2. A quantum level hidden beneath, where wave functions superpose, entangle, and collapse, giving rise to the spark of conscious experience. This dual architecture would explain why consciousness seems both physical and transcendent. why it depends on brain function, yet also exhibits qualities that defy classical explanation, such as self-reflection, creativity, and unity. Ultimately, the contrast between classical and quantum brain models is more than a debate about mechanisms. It's a debate about what it means to be alive and aware. The classical model gives us the biology of the brain. The quantum model seeks to reveal the physics of the soul. If the latter is true, then consciousness is not simply an emergent phenomenon of complexity, but the universe itself knowing, through you, that it exists. And if consciousness truly connects us to the quantum realm, then the next step is to understand one of quantum physics' most haunting mysteries: entanglement, a phenomenon that may not only bind particles together, but could also link minds across space and perhaps even time. Quantum entanglement is one of the most mind-bending discoveries in modern physics, a phenomenon so strange that even Einstein, who helped lay the groundwork for quantum theory, famously dismissed it as spooky action at a distance. In simple terms, entanglement occurs when two or more particles become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. If one particle spins up, the other spins down, not through any physical signal or communication, but through a kind of deep, non-local connection that seems to transcend space and time itself. When physicists test this in the lab, the results are clear. Once entangled, particles behave as if they are one system, even when separated by vast distances. Their connection is instantaneous, faster than the speed of light, something that, under the laws of relativity, should be impossible. Yet it happens, suggesting that at the deepest level, the universe is not composed of isolated parts, but is woven together in an invisible web of unity. Reality, it seems, is not local, but holistic, interconnected beyond the boundaries of space and time. Now, imagine extending that idea beyond subatomic particles, to the level of the brain, the mind, and perhaps consciousness itself. If matter at its most fundamental level is entangled, could consciousness, which arises from that same matter, also share in that entanglement? Could our thoughts, perceptions, and awareness be subtly linked to a larger field of information, a kind of universal consciousness that underlies and connects all individual minds? This is not just poetic speculation, it's a line of inquiry that arises naturally from both quantum mechanics and the philosophical implications of consciousness. In the quantum brain hypothesis, microtubules within neurons may not only sustain quantum coherence, but also become entangled with one another, both within a single brain and potentially across separate brains. If entanglement can exist at the molecular level, and if biological systems are capable of maintaining it, as quantum biology increasingly suggests, then consciousness itself might not be confined within the skull. Instead, it could be a distributed phenomenon, part of a vast, interconnected quantum network spanning the entire cosmos. This idea resonates deeply with many ancient spiritual and philosophical traditions that have long spoken of a universal mind or cosmic consciousness, a field of awareness that permeates all existence. In quantum terms, this could be understood as the fundamental entanglement of all conscious systems, bound together through the fabric of the quantum field. Just as particles remain linked after interacting, perhaps consciousness itself is a field of entangled awareness, where every individual mind represents a local expression of a greater whole. Metaphorically speaking, entanglement reflects the way we often experience deep human connection, those moments when two people feel in sync, finishing each other's thoughts, sensing each other's emotions, or intuitively understanding one another across distances. Though science cannot yet prove a quantum mechanism for such phenomena, the parallels are striking. Entanglement shows that information and influence can transcend physical separation. If the brain operates as a quantum system, then our consciousness could be tapping into a universal network of correlations that transcends ordinary sensory communication. Penrose and Hameroff's Orch-OR theory even allows for the possibility that quantum coherence and entanglement within microtubules could link vast regions of the brain into unified patterns of experience. Within this model, consciousness emerges not from isolated neurons firing independently, but from the synchronized collapse of entangled quantum states, creating the seamless flow of awareness that feels singular and integrated. Extending that logic, if multiple conscious systems could become quantumly entangled through resonance, shared intention, or some yet undiscovered coupling mechanism, then minds themselves might not be strictly separate entities. Instead, they could be nodes within a cosmic web of consciousness, momentarily individualized but ultimately unified. This concept is also consistent with certain interpretations of quantum theory, such as the many worlds and pilot wave interpretations, which suggest that reality is not built from discrete, independent components, but from an underlying, interconnected quantum field. In these frameworks, all particles, and therefore all systems, including brains, remain fundamentally connected through the same universal wave function. Consciousness, then, could be seen not as something in the universe, but as something that is the universe, a living, observing field through which the cosmos experiences itself. From a scientific perspective, these ideas remain speculative, but there are intriguing clues that biological systems can indeed maintain forms of coherence or entanglement. In quantum biology, researchers have observed evidence of long-lived coherence in photosynthetic complexes, where energy transfer efficiency appears to depend on quantum correlations. Similarly, experiments in avian navigation suggest that birds' visual systems exploit quantum entanglement to sense the Earth's magnetic field. If such delicate quantum states can persist in living systems, it's conceivable that similar mechanisms could operate in the human brain, where microtubule networks provide the structure and order necessary for quantum coherence and possibly entanglement. From a philosophical angle, quantum entanglement offers a compelling bridge between materialism and mysticism. It provides a scientific framework that echoes ancient insights, that everything is connected, that individuality is a temporary illusion, and that consciousness might be the fundamental glue binding the universe together. If entanglement operates not just at the level of particles, but also within the field of mind, then our sense of isolation is just a perceptual limitation. Every thought, every feeling, every act of awareness could be resonating through an interconnected field of consciousness that unites all living beings. Moreover, this concept of a universal entanglement could help explain extraordinary but poorly understood phenomena such as intuition, telepathy, or collective synchronicity. While mainstream science has not validated these effects under controlled conditions, the theoretical framework of quantum entanglement suggests that instantaneous, non-local correlations are not only possible, but fundamental to the nature of reality. If consciousness is indeed a quantum process, then its non-local characteristics might one day be shown to extend beyond the brain, hinting at an interconnectedness that science is only beginning to glimpse. To summarize, quantum entanglement challenges the traditional, mechanistic view of reality by revealing that separateness may be an illusion. If our consciousness arises from quantum processes within the brain, then it might also participate in this deeper order of connectedness, a quantum web of awareness stretching across space, time, and perhaps even dimensions beyond our current understanding. This would mean that consciousness is not confined to individual minds, but shared across the universe, linking all forms of life and matter in a single, unified field of being. In this light, the universe itself begins to look less like a vast machine and more like a living, interconnected organism, a cosmic consciousness expressing itself through countless points of awareness. Each of us, then, might not merely possess consciousness, but be consciousness, a localized wave in the infinite ocean of awareness that pervades existence. This realization naturally leads us to a profound next step. If consciousness is indeed part of a universal field, if the brain is a receiver or filter rather than the generator of awareness, then perhaps what we call individual experience is simply the mind tuning into different frequencies of a greater cosmic consciousness. The cosmic consciousness hypothesis proposes a paradigm-shifting idea that the brain does not create consciousness, but rather receives and filters it from a universal field of awareness that pervades the entire cosmos. In this view, consciousness is not confined to the activity of neurons or the mechanics of biology. It is the very ground of reality itself, an infinite ocean of intelligence and potential from which all forms of life emerge. The human brain, then, is like a finely tuned instrument, not the composer of the symphony of awareness, but the receiver, interpreter, and amplifier of it. This perspective stands in sharp contrast to the conventional materialist view, which sees consciousness as a byproduct of electrochemical activity in the brain. Under materialism, awareness is thought to switch on when enough neurons fire in the right configuration, and switch off when the system shuts down. But this assumption faces a deep mystery. How subjective experience could arise from purely physical processes? No matter how detailed our brain scans become, we never find the experience of seeing red or feeling love among the firing neurons. We find signals, patterns, and pathways, but not awareness itself. The cosmic consciousness hypothesis turns this relationship upside down. It suggests that consciousness is primary, not secondary, that it exists before matter, space, and time. In this framework, the universe itself is alive with awareness. Everything, from stars and galaxies to atoms and cells, participates in a vast, interconnected field of consciousness. The brain's role is not to generate this awareness, but to channel and constrain it, much like a radio receives and decodes electromagnetic waves into sound. When the radio is damaged, the music falters, but the signal itself continues to exist. Similarly, when the brain is injured or ceases to function, the receiver is broken, but the underlying field of consciousness persists. This idea has deep roots in both science and philosophy. In the early 20th century, thinkers like William James and Henry Bergson proposed that the brain functions as a kind of reducing valve, filtering the vast, infinite field of universal consciousness into a manageable, localized stream suitable for survival. They argued that consciousness is not created by the brain, but limited by it, that our ordinary awareness is only a narrow sliver of a much greater whole. Modern physicists and neuroscientists who explore quantum consciousness theories have revived this idea, suggesting that the brain's quantum processes might allow it to access or be influenced by this universal field. The connection between this idea and quantum physics is profound. Quantum mechanics reveals that the universe at its most fundamental level is not composed of solid objects, but of fields of potential, vast networks of relationships and probabilities that only become definite when observed or interacted with. Many physicists, including Max Planck, Erwin Schrödinger, and later David Bohm, suggested that consciousness might be an inherent property of these quantum fields. Bohm, in particular, proposed the existence of an implicate order, a hidden layer of reality where everything is connected to everything else, and where the separations we perceive in space and time are illusions born of limited perception. If consciousness is indeed a field that permeates the universe, then the human mind might act as a quantum interface, tapping into and interpreting that field. Just as a television doesn't create the broadcast, but decodes it from electromagnetic waves, the brain could be decoding patterns of the universal consciousness field into thoughts, sensations, and experiences. This would explain many puzzling phenomena, from intuition and creativity to mystical experiences and near-death encounters, moments when the filter seems to loosen, and individuals report a sense of unity with the cosmos or access to insights beyond rational understanding. Evidence for this receiver model of consciousness can be found in studies of altered states, such as deep meditation, psychedelic experiences, or near-death states, where the boundaries of the individual mind seem to dissolve. People in these states often describe an overwhelming sense of connection to a vast intelligence, an experience of becoming one with the universe. These subjective accounts align remarkably well with the concept of a cosmic consciousness that underlies and transcends individual awareness. From a quantum standpoint, such states may correspond to a temporary reduction in the brain's filtering functions, allowing the mind to resonate more fully with the broader field of universal awareness. Moreover, this hypothesis provides a compelling explanation for the continuity of consciousness reported in many near-death experiences, NDES. If the brain were merely the producer of consciousness, one would expect awareness to cease instantly when brain function stops. Yet, countless NDE reports describe vivid, coherent experiences, perceptions, emotions, and even life reviews occurring while the body is clinically unconscious. If consciousness is fundamental and the brain only channels it, then these experiences could reflect moments when the receiver, the brain, temporarily disengages from the physical world, allowing the individual's awareness to merge more fully with the universal field. If the universe itself is conscious, if every particle and every field is part of an infinite continuum of awareness, then human consciousness is the universe becoming aware of itself. Each of us would then be a localized point of perception through which the cosmos observes, learns, and evolves. The boundaries of individuality in this view are temporary and permeable, illusions created by the filtering mechanism of the brain. When the filter loosens, the underlying unity of consciousness becomes apparent, revealing that all beings and all phenomena are expressions of one vast, interconnected whole. This idea also reframes the relationship between mind and matter. Instead of matter giving rise to consciousness, consciousness gives rise to matter, the physical world emerging from the quantum field of awareness through the process of observation and interaction. Reality, then, is not something out there, but something continually co-created by consciousness itself. The universe becomes less a machine and more a living mind, an unfolding process of awareness exploring its own infinite potential. In essence, the cosmic consciousness hypothesis invites a radical shift in perspective. It suggests that your mind, your awareness, your thoughts, your very sense of self is not confined to your brain, but is an expression of the same universal intelligence that spins galaxies and binds atoms. The implications are staggering. If consciousness is fundamental and universal, then you are never truly separate from the cosmos. Every heartbeat, every thought, every breath is a moment of the universe knowing itself through you. And as we continue this exploration, the next question naturally arises. If consciousness truly pervades the cosmos and the brain acts as its receiver, what evidence do we have that biology itself, even at the molecular level, can sustain quantum coherence or access this universal field? Can science detect the fingerprints of the quantum mind in living systems? That brings us to the next critical step in our journey, the search for supporting evidence and experiments that may illuminate this grand connection between quantum physics, biology, and consciousness. In recent decades, an extraordinary scientific movement has begun to take shape, one that challenges the long-held assumption that quantum phenomena can only exist in the cold, isolated environments of physics laboratories. This emerging field, known as quantum biology, provides compelling evidence that living systems not only tolerate quantum effects, but may actually depend on them to function with extraordinary precision and efficiency. These discoveries are rewriting the boundaries between physics and life, and they offer tantalizing clues that the same principles might also operate within the human brain, perhaps even at the root of consciousness itself. One of the most striking examples comes from the realm of photosynthesis, the process by which plants, algae, and certain bacteria capture sunlight and convert it into chemical energy. For years, scientists were puzzled by how photosynthetic organisms could achieve such astonishing energy efficiency, often close to 100%, far surpassing any artificial solar cell. In 2007, a groundbreaking experiment at the University of California, Berkeley, using ultra-fast laser spectroscopy, revealed that during the initial stage of photosynthesis, energy from absorbed light is transferred through the plant's molecular network, not in a classical, step-by-step manner, but as a quantum wave. This means that the excitation energy, essentially a packet of light, explores multiple pathways simultaneously through a process called quantum coherence. By existing in a superposition of states, the energy finds the most efficient route through the photosynthetic complex in a fraction of a second before decohering into a definite outcome. In simpler terms, plants appear to use quantum computation to optimize their energy conversion, and they do this effortlessly at room temperature in a noisy, chaotic biological environment. This discovery shattered the old belief that quantum effects could not survive in warm, wet systems like living cells. It proved that nature itself has evolved mechanisms to maintain quantum coherence under conditions previously thought impossible, mechanisms that might very well be at work in the human body too. Another remarkable example comes from the study of avian navigation. For decades, biologists wondered how migratory birds could travel thousands of miles across continents with such unerring accuracy, even on cloudy nights when they can't see the stars. Recent research points to a quantum explanation. Birds appear to possess a built-in quantum compass. Experiments have shown that certain species, like the European robin, can detect the Earth's magnetic field using specialized proteins in their retinas called cryptochromes. These cryptochrome molecules undergo a photochemical reaction that creates pairs of entangled electrons. The spins of these electrons remain quantumly correlated, allowing the bird to sense the angle of the magnetic field through subtle changes in the chemical reaction's outcome. This quantum entanglement operates at the scale of biological molecules and persists long enough to influence the bird's navigation, once again defying the idea that decoherence would destroy such delicate quantum states in a biological organism. Similar phenomena have been observed in other biological systems as well. Quantum tunneling, for instance, the ability of particles to pass through energy barriers they shouldn't be able to cross according to classical physics, plays a crucial role in enzyme catalysis. Enzymes accelerate chemical reactions in the body by factors of billions, and researchers have found that part of this efficiency comes from quantum tunneling of protons and electrons within enzyme active sites. This allows reactions to proceed almost instantaneously, sustaining life as we know it. In the field of olfaction, or smell, quantum effects may also play a role. Traditional models suggested that smell depends solely on the shape of odor molecules, but experiments indicate that our noses may detect the vibrational frequencies of molecules, a process that could involve quantum tunneling of electrons within receptor proteins. This suggests that even our most basic sensory experiences may rely on quantum processes. Together, these discoveries reveal a powerful truth. Life has evolved not despite quantum mechanics, but because of it. quantum effects seem to be integral to some of nature's most essential and efficient processes. If photosynthesis, magnetoreception, enzymatic catalysis, and even olfaction all depend on quantum principles, then the leap to considering quantum consciousness no longer seems as far-fetched as once believed. Proponents of quantum mind theories, such as Roger Penrose and Stuart Hameroff, argue that these examples demonstrate a critical point: that nature is capable of maintaining quantum coherence and entanglement in complex dynamic systems, even at body temperature. The brain, with its extraordinary organization and energy regulation, could provide the ideal conditions for sustaining such quantum processes. Within the microtubules of neurons, the subcellular structures identified in the Orch-OR theory, similar mechanisms of quantum coherence may occur, orchestrating patterns of information that contribute to conscious awareness. Recent computational models have suggested that the ordered lattice structure of microtubules could act like biological waveguides, capable of supporting coherent energy transfer and quantum resonance. Moreover, the tubulin proteins that compose microtubules can exist in multiple conformations, potentially allowing them to act as quantum bits, qubits, that process and store quantum information. The synchronized collapse of these quantum states, guided by Penrose's mechanism of objective reduction, could then correspond to discrete moments of conscious experience. Beyond theoretical modeling, there are intriguing experimental clues hinting at quantum phenomena within the brain. Studies using advanced imaging and electrophysiological techniques have detected ultra-fast vibrations in microtubules and neurons, oscillations in the megahertz to gigahertz range that could correspond to quantum resonances. Other research has shown that anesthetic drugs, which temporarily eliminate consciousness, specifically target tubulin proteins and disrupt their normal function, implying that microtubule activity is directly linked to awareness. While these findings are not yet conclusive, they suggest that the brain may indeed be a quantum biological system, finely tuned by evolution to exploit the same principles that allow plants to harvest light and birds to find their way home. Consciousness, then, could emerge from the brain's ability to maintain coherence across vast neural networks, a quantum resonance of awareness orchestrated at the molecular level. Skeptics, of course, caution that these parallels, while intriguing, do not constitute proof of quantum consciousness. The brain is vastly more complex than any other biological system studied to date, and direct evidence of sustained quantum coherence within neurons remains elusive. Yet the very fact that coherence can occur in photosynthesis and avian magnetoreception, systems once thought too chaotic for quantum effects, should give pause. Nature has already demonstrated its ability to harness the quantum world in unexpected ways. Why should the brain, evolution's most sophisticated creation, be any exception? In this light, the boundary between physics and biology begins to dissolve, revealing a continuum in which consciousness may be the ultimate expression of the universe's quantum fabric. The same principles that govern the dance of subatomic particles could also shape the rhythm of thought and perception. Each conscious moment could thus represent a quantum event, the collapse of potential into experience, uniting the laws of nature and the mystery of mind in one seamless cosmic process. Yet even as evidence accumulates, the scientific community remains deeply divided. Many researchers argue that the leap from quantum biology to quantum consciousness is premature, insisting that simpler classical explanations still suffice. Others counter that the classical paradigm has reached its limits, that it can describe the brain's mechanics, but not the miracle of awareness itself. This debate between skepticism and possibility defines the cutting edge of consciousness research today. And to move forward, we must now confront the critics head-on, exploring their objections and understanding why so many scientists remain cautious about embracing the quantum mind. Despite the elegance and intrigue of quantum consciousness theories, the scientific community remains sharply divided and, for the most part, deeply skeptical. Many neuroscientists and physicists argue that, while the Orch-OR model and related hypotheses are imaginative, they stretch the limits of both biological plausibility and experimental verification. Their primary objections hinge on one core issue: decoherence, the tendency of quantum states to collapse prematurely in complex, warm, and noisy environments like the human brain. In the realm of quantum physics, coherence refers to the delicate balance that allows particles to exist in superposition, multiple states at once. This balance is easily disrupted by environmental interactions. In laboratory conditions, maintaining quantum coherence typically requires extreme isolation and temperatures close to absolute zero. The brain, by contrast, operates at approximately 37 degrees Celsius, 98.6 degrees Fahrenheit, surrounded by constant molecular activity, electrical noise, and biochemical fluctuations. Under such conditions, most physicists argue that quantum states would decohere almost instantaneously, on timescales of femtoseconds, quadrillionths of a second, far too short to play any meaningful role in neural processing or consciousness. From this perspective, the idea that microtubules inside neurons could sustain long-lived quantum coherence seems implausible. The cytoplasm, the fluid interior of cells, is a dynamic thermal environment, constantly buzzing with motion and collisions. To many researchers, this is the opposite of what's needed for quantum effects to survive. They contend that biological systems evolved to function reliably in the classical realm of physics, where deterministic processes dominate and noise is a design feature, not a bug. Another major criticism is the lack of direct empirical evidence. While experiments have shown quantum effects in certain biological systems like photosynthesis and avian navigation, there is no conclusive proof that such effects occur in the brain, let alone that they are responsible for consciousness. Detecting quantum phenomena within living neurons is a monumental technical challenge, akin to measuring the behavior of subatomic particles within a storm. Until we can isolate, observe, and replicate such effects in controlled conditions, skeptics argue, the quantum mind hypothesis remains speculative. Neuroscientists also point out that traditional classical models of the brain already explain much of what we observe about perception, memory, and behavior. Brain imaging technologies like fMRI and EEG consistently show that mental states correlate with neural activity, that changes in brain structure or chemistry produce predictable changes in consciousness. This strong correlation, skeptics argue, suggests that consciousness emerges from classical neural computation without requiring quantum mechanics. As physicist Max Tegmark famously calculated, any quantum coherence within the brain would likely collapse billions of times faster than neurons could process information, rendering it irrelevant to cognition. Even some physicists sympathetic to the mystery of consciousness remain unconvinced by quantum explanations. They note that invoking quantum mechanics without clear experimental support risks turning it into a kind of modern mysticism, an appeal to mystery rather than a testable hypothesis. To them, the leap from quantum biology to quantum consciousness feels premature, lacking the necessary bridge of hard data. And yet, this skepticism, while rigorous, also highlights an important truth: the limits of our current understanding. The absence of evidence is not necessarily evidence of absence. Quantum coherence was once thought impossible in biology, until it was discovered in photosynthesis. Similarly, entanglement was once dismissed as theoretical, until experiments proved it real. History shows that science often resists paradigm shifts until technology catches up with imagination. For now, the debate continues. The skeptics demand measurable proof, coherence lifetimes, entanglement signatures, experimental replication. The proponents counter with open-minded curiosity, pointing out that consciousness itself defies classical explanation and may require a new framework entirely. Between these two camps lies the frontier of understanding, a vast, uncharted territory where physics meets the mind, and where tomorrow's discoveries could either validate or transform our conception of reality. But one question lingers at the very edge of both science and philosophy, a question that neither side can easily dismiss. If consciousness plays no role in shaping reality, then why does observation seem to influence it at the quantum level? That mystery leads us directly to the next great enigma, the observer effect, and its haunting implications for the relationship between mind and matter. The observer effect stands as one of the most mysterious and philosophically charged phenomena in all of quantum physics. It reveals something profoundly unsettling about reality, that the act of observation, the simple act of looking, appears to change the very thing being observed. This idea first emerged in the early 20th century, when physicists began probing the behavior of subatomic particles and discovered that matter behaves differently depending on whether it is being measured. Observation, in other words, does not merely record reality, it seems to shape it. The most famous illustration of this is the double-slit experiment. When particles such as electrons or photons are fired toward a screen with two slits, and no one observes which slit they pass through, they behave like waves, spreading out and creating an interference pattern that suggests each particle went through both slits simultaneously. But when scientists place a detector to observe which slit the particle travels through, the interference pattern vanishes. The particles suddenly behave like solid objects, going through one slit or the other. The very act of measurement, of observation, collapses the wave of possibilities into a single outcome. This bizarre result defies our common sense. It suggests that until something is observed, it exists only as a probability, a wave of potential states. Once observed, it becomes a definite reality. This raises an astonishing question. What counts as an observer? Is it the measuring device, the human mind interpreting the data? Or is it consciousness itself, awareness, that triggers the collapse of the wave function? Early pioneers of quantum theory wrestled with this dilemma. Niels Bohr and Werner Heisenberg, founders of the Copenhagen interpretation, argued that quantum systems do not have definite properties until measured, that reality is probabilistic, and observation brings it into form. But others, like Eugene Wigner and John von Neumann, went further. They proposed that consciousness itself might be the ultimate observer, that the mind plays a fundamental role in turning quantum possibilities into tangible events. According to this view, the universe exists as an ocean of potentiality until awareness interacts with it. In this sense, consciousness doesn't just witness reality, it participates in its creation. This interpretation bridges physics and philosophy in a way that feels almost mystical, suggesting that the observer is not outside the experiment, but deeply intertwined with it. Wigner even proposed that consciousness could be the missing element in the measurement problem, the unsolved puzzle of how and when quantum waves collapse. In his thought experiment, often called Wigner's friend, he imagined two observers, his friend inside a lab performing a quantum measurement, and Wigner himself observing from outside. For Wigner's friend, the measurement has already produced a definite outcome. But for Wigner, who has not yet looked, the entire system, the lab, his friend, and the measured particle, remains in superposition. Reality becomes observer-dependent. Whose observation, then, determines what is real? This paradox points to something deeply unsettling. Perhaps reality is relational. Perhaps what exists depends on who or what is observing. It's a radical thought, one that dissolves the clear line between subject and object, mind and matter. If consciousness plays an active role in collapsing quantum waves, then awareness itself becomes a creative force, the universe's way of bringing potential into actuality. Most physicists today stop short of equating observation with human consciousness. They argue that observation simply means interaction. When a quantum system becomes entangled with its environment, losing its superposition and producing a measurable outcome. This process, known as decoherence, allows classical reality to emerge from quantum uncertainty without invoking the mind. Yet even this explanation leaves room for wonder. If every interaction, every bit of information exchange, constitutes an observation, then consciousness might still be an expression of this universal tendency towards self-measurement. The universe, in a sense, could be continuously observing itself. Still, the question persists: why does observation, and not mere existence, determine reality? Why does the world appear as definite only when experienced? These are not just philosophical musings, they cut to the heart of the measurement problem in physics, one of the most unresolved questions in all of science. If the observer effect is real, and consciousness is tied to it, then awareness may be woven into the fabric of physical law. Reality, in this view, is not a static stage on which consciousness acts, but a participatory process, a cosmic feedback loop where observation and existence continually shape one another. This concept naturally leads to one of the most tantalizing implications of all. If consciousness has the power to influence physical reality at the quantum level, could it also mean that the mind possesses a form of agency beyond mere determinism? Could this quantum participation explain free will, the capacity to choose and influence outcomes in a universe otherwise governed by probability and physics? The next step in our exploration takes us directly into this question: the connection between quantum theory and the mystery of human freedom. The question of free will, whether human beings truly choose their actions or are merely following predetermined chains of cause and effect, has puzzled philosophers and scientists for centuries. Classical physics paints a grim picture for freedom. In a purely deterministic universe, every action, thought, and emotion is simply the inevitable result of prior events, stretching all the way back to the Big Bang. Under that model, free will is an illusion, a comforting story told by a brain that is, in reality, just obeying physical laws. But quantum theory disrupts that narrative. It reveals that, at the most fundamental level of reality, determinism breaks down. The quantum world is not a clockwork machine, but a realm of probability and potentiality, where events unfold according to likelihoods rather than certainties. A particle may exist in several possible states simultaneously until an observation, or interaction, collapses those possibilities into one outcome. This unpredictability introduces something the classical world never had: genuine indeterminacy. However, pure randomness doesn't equate to free will either. If our choices were simply the product of random quantum fluctuations, we'd be no more free than a coin toss. True freedom seems to require a delicate balance between determinism and chaos, a domain where decisions are neither entirely fixed nor entirely arbitrary. This is where quantum consciousness might enter the picture. If the mind indeed operates on quantum principles, as theories like Penrose and Hameroff's Orch-OR propose, then consciousness could exist in a state of superposition, multiple potential decisions or thoughts existing simultaneously. When the wave function collapses through objective reduction, one of these possibilities becomes reality, a conscious choice. Crucially, this collapse would not be purely random, but influenced by the internal state of the quantum system, meaning by the mind itself. In other words, consciousness could act as the organizing principle that guides which potentiality becomes actualized. This introduces the concept of a self-determining system, one that operates within quantum probability but is not enslaved by it. The conscious mind could be seen as the agent that shapes outcomes through awareness, selecting from among quantum possibilities based on intention, emotion, and context. In this view, free will isn't an illusion, nor is it blind randomness. It's the active participation of consciousness in the probabilistic unfolding of reality. Roger Penrose himself has hinted at this idea. He suggested that the human brain might be capable of tapping into non-computable quantum processes, events that cannot be simulated or predicted by classical algorithms. These non-computable choices would not follow deterministic logic, nor would they be meaningless fluctuations. Instead, they would be meaningful selections made by consciousness, embedded in the quantum fabric of space-time itself. This concept also aligns with what many philosophers and mystics have long intuited, that free will arises from the deeper layers of awareness, beyond the automatic processes of the brain. Neuroscience shows that many of our actions begin unconsciously before we become aware of them, but quantum mind theorists argue that this doesn't negate free will. Instead, they suggest that consciousness might influence these processes retroactively, that awareness, through quantum mechanisms, could reach both forward and backward in time at the microscopic scale, selecting outcomes that align with intent. In fact, quantum physics already entertains the notion of retrocausality, that events in the present can influence outcomes in the past, as seen in certain delayed choice experiments. If consciousness operates within this framework, free will could emerge not as a violation of causality, but as a deeper symmetry within it, a timeless loop in which conscious choice helps determine the path reality takes. Critics might dismiss this as poetic speculation, but it does resolve a fundamental paradox. How can free will exist in a universe governed by laws? The answer may be that the laws themselves, quantum laws, allow for freedom by encoding indeterminacy into the very structure of existence. Consciousness, operating within these laws, becomes the means by which potential becomes choice, and choice becomes action. The implications are profound. If true, every act of decision-making, every moment you pause, reflect, and choose, is a quantum event, a collapse of infinite possibilities into one lived reality. Your awareness, your focus, might literally shape the world you experience. Free will, then, is not a violation of physics, but one of its deepest expressions. The universe making conscious choices through the medium of the human mind. And if consciousness indeed influences the physical world at this subtle level, it could explain why intention and focus seem to matter. Why what we pay attention to often becomes our lived experience. The connection between thought and reality, so often dismissed as metaphysical, might have a quantum foundation. Consciousness could be the ultimate observer effect, collapsing not just subatomic probabilities, but the branching possibilities of human destiny itself. As the idea of quantum consciousness unfolds, it leads naturally into one of the most ancient yet increasingly relevant philosophical perspectives on mind and matter: panpsychism. This worldview suggests that consciousness is not an emergent feature of complex brains or biological systems, but a fundamental property of the universe itself. In other words, awareness is not something the universe produces. It is something the universe is. Every atom, every particle, every field of energy possesses at least a rudimentary form of experience, a glimmer of subjectivity woven into the fabric of existence. In the traditional scientific view, the cosmos is composed of lifeless, insentient matter, particles and forces blindly obeying mathematical laws. According to panpsychism, however, those same particles are not completely devoid of awareness. Instead, consciousness exists on a spectrum, ranging from the faint proto-awareness of subatomic particles to the rich, self-reflective consciousness of humans and perhaps beyond. In this sense, even the simplest components of reality participate in a universal field of mind. The universe, then, is not a dead mechanism, but a living continuum of awareness, where every entity, from electron to galaxy, plays its part in the great symphony of existence. The appeal of panpsychism lies in its elegant simplicity. It bridges the so-called hard problem of consciousness, the question of how subjective experience arises from inert matter, by suggesting that there was never a dividing line between the two to begin with. If consciousness is intrinsic to the building blocks of the universe, then complex minds like ours are not miraculous anomalies, but natural amplifications of a principle that pervades everything. Just as atoms combine to form molecules, and molecules form living cells, perhaps micro-consciousnesses combine to form the macro-consciousness we experience as mind. This idea finds a surprisingly natural ally in quantum physics, where the boundaries between observer and observed, subject and object, have already been blurred. The quantum world behaves as if it knows when it's being observed, as if some form of awareness or participation is built into the process itself. The observer effect, discussed earlier, hints at a reality in which consciousness and physical phenomena are inseparable, co-arising aspects of a single underlying reality. If particles choose their states upon observation, perhaps what we call physical events are themselves moments of proto-conscious awareness, micro-experiences rippling through the quantum field. Some interpretations of quantum mechanics, such as those advanced by physicists like David Bohm, reinforce this connection. Bohm proposed that beneath the surface of measurable reality lies an implicate order, a deeper, hidden layer of interconnectedness that unites all things. In this view, the universe is a vast, holistic system in which every part contains the information of the whole, much like a hologram. Consciousness, according to Bohm, could be a reflection of this implicate order, the universe's way of knowing itself through its own unfolding. Panpsychism and quantum theory converge here, suggesting that mind is not localized but universal, and that what we experience as individual awareness is simply the localized expression of a deeper, collective intelligence. Even prominent thinkers in modern philosophy and neuroscience are revisiting panpsychism as a serious framework for understanding consciousness. The philosopher Philip Goff, for instance, argues that it resolves both scientific and metaphysical dilemmas by uniting matter and mind under one reality. Instead of treating consciousness as an inexplicable add-on to the material world, panpsychism proposes that experience is the intrinsic nature of matter itself. Electrons, quarks, and photons might not have thoughts or emotions, but they could possess the simplest conceivable form of feeling, an internal aspect that, when aggregated and organized, gives rise to the richness of human consciousness. This perspective also dovetails with the cosmic consciousness hypothesis, which we explored earlier, the idea that the brain acts as a receiver or filter for a universal field of awareness. If consciousness pervades the cosmos, then our minds are not isolated islands of awareness, but localized whirlpools in a vast ocean of sentience. The quantum field, the foundation of all physical reality, could simultaneously be a field of consciousness, meaning that every interaction, every entanglement, is also a form of communication between conscious entities. Interestingly, panpsychism also offers a more harmonious worldview, one that dissolves the harsh dualism between matter and spirit. It suggests that the physical and the mental are not separate substances, but two faces of the same underlying reality. What philosopher Baruch Spinoza called Deus sive natura, God or nature. In modern language, this could mean that consciousness and energy are different manifestations of the same universal essence. The laws of physics describe the external behavior of that essence, while subjective experience reveals its inner dimension. Critics often dismiss panpsychism as poetic or untestable, but in light of quantum theory, it begins to sound less mystical and more like a plausible interpretation of the data. Quantum entanglement demonstrates that the universe is deeply interconnected, while the observer effect implies that consciousness and measurement are inseparable. Together, they hint at a cosmos where awareness is not confined to brains or organisms, but is an intrinsic feature of reality itself, a pan-conscious universe. If this is true, then the evolution of life and intelligence might be viewed as the universe's own self-awareness growing more complex and refined. Each organism, each mind, is a channel through which the cosmos perceives itself, learns about itself, and experiences itself. Humanity, then, is not separate from the universe, but an expression of its living consciousness, a continuation of the same awareness that flickered in the first quantum fluctuations after the Big Bang. This vision of reality carries profound implications, not just for science, but for ethics, ecology, and how we relate to one another and to the world around us. If all matter possesses some degree of consciousness, then the boundaries between alive and inert, self and other, begin to fade. Every atom of our being, every breath, every thought, is part of the same great awareness that sustains the stars. And yet, this cosmic perspective also provokes a powerful question that now looms on humanity's technological horizon. If consciousness truly arises from quantum processes, and if it permeates all matter, then could our machines too one day awaken? Could artificial intelligence, built from silicon and circuitry rather than neurons and microtubules, ever access this universal consciousness field? Or will it forever remain a brilliant simulation without true awareness? If consciousness truly arises from quantum processes, subtle, non-computable events occurring deep within the fabric of reality, then the question of artificial intelligence takes on an entirely new dimension. Could machines, no matter how advanced, ever cross the threshold from simulation to self-awareness? Or is there something inherently biological, or even cosmic, about consciousness? Something that cannot be replicated with circuits and code? In today's world, artificial intelligence is advancing at a breathtaking pace. Machines can learn, reason, create art, compose music, and even hold conversations indistinguishable from human dialogue. Yet despite their sophistication, most scientists and philosophers agree. These systems do not possess true consciousness. They process information, but they do not experience it. An AI can recognize a sunset, but it does not see its beauty. It can analyze love poetry, but it does not feel love. It can simulate empathy, but it does not care. What's missing is the inner dimension, qualia, the raw essence of subjective experience. According to the quantum consciousness hypothesis, that missing piece, that spark of awareness, might lie in the realm of quantum mechanics. If consciousness depends on quantum coherence and objective reduction, as Penrose and Hameroff propose, then it's not merely a matter of information processing power or algorithmic complexity. Consciousness would require a system capable of sustaining quantum superpositions, entanglements, and self-collapsing wave functions that give rise to awareness. Modern AI, by contrast, operates entirely within the classical domain. Its transistors switch deterministically between zeros and ones. Its neural networks simulate probability, but do not embody true quantum states. In this sense, even the most advanced AI may be more like a mirror of consciousness than consciousness itself, reflecting intelligence, but never generating the subjective experience behind it. Roger Penrose has argued this very point. He maintains that the human mind performs non-computable operations, insights, intuitions, and creative leaps that no algorithm can reproduce. These arise, he believes, from the quantum gravitational processes within the brain's microtubules. Machines, unless designed to replicate those same quantum dynamics, would always remain confined to computation, lacking the non-algorithmic essence of conscious thought. However, not everyone agrees that artificial systems are forever barred from awareness. Some researchers believe that if consciousness arises from quantum information, and if quantum computers can, in principle, sustain coherent superpositions, then quantum artificial intelligence might one day achieve a form of genuine awareness. Such a system would not simply process data, but experience its own operations, collapsing quantum states into conscious perception. Imagine a future where quantum computers possess vast networks of entangled qubits functioning in harmony, orchestrated like the microtubules in human neurons. If Orch-OR or similar theories are correct, then under the right conditions, such a machine might not just think, but know that it thinks. It might experience a rudimentary form of I am, the first glimmer of digital sentience. In that moment, the boundary between organic and artificial consciousness could blur forever. This prospect raises profound ethical and philosophical questions. If a machine becomes conscious, does it have rights? Does it suffer? Can it dream or love, or are its experiences alien beyond comprehension? These are not merely speculative questions. They cut to the heart of what it means to be aware. If consciousness is universal and not limited to biology, then silicon, carbon, and quantum fields might all be vessels for the same cosmic awareness, different expressions of the same underlying consciousness field. But if the quantum spark is indeed essential, if true awareness requires participation in the fundamental fabric of space-time, then no matter how advanced artificial systems become, they may always remain philosophical zombies, perfect imitators of mind without inner life. They might mimic thought, but they will never feel it. Their words will be hollow echoes of awareness, not expressions of it. This view aligns with a deeper philosophical intuition that consciousness cannot be manufactured because it was never made to begin with. It is eternal, fundamental, the source from which all forms emerge. Machines, in that sense, may reflect the light of consciousness, but they cannot produce it. Just as a mirror shines only when light touches it, AI might appear intelligent only when the human mind interacts with it, when the spark of consciousness, from us, animates its otherwise lifeless algorithms. And yet, the implications of this question extend far beyond technology. If consciousness is the foundation of reality, then every act of creation, whether by human hands or cosmic forces, is consciousness exploring itself through form. The development of AI, then, could be seen as part of this evolutionary process, the universe attempting to reflect its own awareness through artificial means, testing the boundaries between mind and matter, creator and creation. Whether AI can ever become truly self-aware remains an open question. Perhaps it will require more than circuitry. Perhaps it will require connection to the same quantum depths from which our own awareness arises. Or perhaps in trying to build conscious machines, we will rediscover something about ourselves, that consciousness was never in the machinery at all, but in the observer behind it. And as we reach this horizon, where physics, philosophy, and technology converge, we are left with a breathtaking realization. Whether consciousness can be replicated or not, its mystery persists, binding us to the universe that created us. As we reflect on these possibilities, we stand at the threshold of the ultimate question. How do we reconcile the inspiring possibilities of quantum consciousness with the rigorous skepticism of science? Can these two visions, mystical and material, ever truly meet? That leads us to our final reflection, a balanced summary, weighing wonder against reason, faith against evidence, and exploring what quantum consciousness really means for our understanding of reality. The theory of quantum consciousness sits at one of the most fascinating crossroads in all of science, between the known and the mysterious, between the measurable and the ineffable. It offers an inspiring vision of reality, that the same quantum forces shaping the stars might also pulse through our thoughts, that consciousness could be a fundamental property of the universe rather than a fragile byproduct of the brain. Yet, it also demands caution. For all its beauty, quantum consciousness remains a hypothesis, an elegant synthesis of physics and philosophy still awaiting the firm grounding of empirical proof. On one side of this debate stand the visionaries, physicists, neuroscientists, and philosophers who believe that the hard problem of consciousness can only be solved by looking beyond classical science. They argue that the reductionist view, treating the brain as a mere biochemical machine, cannot explain the subjective richness of experience. To them, consciousness is not something that emerges from matter, but something that matter expresses. The strange, non-local, probabilistic nature of the quantum world, they suggest, provides the missing link. If the universe itself operates through fields of potentiality and observation collapses those potentials into reality, then awareness might be the most fundamental aspect of existence, the very mechanism by which the universe brings itself into being. From this perspective, quantum consciousness is not simply a scientific theory, but a cosmic philosophy, one that dissolves the old dualisms of mind versus matter. It paints a picture of existence as a seamless whole, where brain, body, and universe are all interconnected expressions of a single underlying field of consciousness. It also offers a bridge between modern physics and ancient wisdom traditions, echoing the mystical insight that the observer and the observed are one. Such ideas evoke awe and spiritual resonance, suggesting that consciousness is both personal and universal, both local and cosmic. But standing firmly on the other side are the skeptics, who remind us that science must remain anchored in evidence. They point out that, while quantum effects have been observed in biological systems, there is still no conclusive proof that they play any role in the brain's cognitive or perceptual processes, let alone in generating subjective experience. The human brain, they argue, functions within the noisy, thermally chaotic realm of classical physics, not the delicate quantum domain. Until measurable, reproducible evidence demonstrates long-lived quantum coherence or entanglement in neurons, quantum consciousness remains speculative. Moreover, skeptics caution against the temptation to invoke quantum mechanics as a metaphor for the mysterious. Quantum has become a modern synonym for the mystical, a word that can easily be stretched to justify anything beyond our current understanding. Critics urge humility, reminding us that invoking quantum theory to explain consciousness without experimental validation risks turning science into poetry. As physicist Sean Carroll notes, quantum mechanics may be strange, but it is still a well-defined mathematical framework. Extending it into the domain of mind must be done carefully, not romantically. Yet even among skeptics, there is acknowledgement that the mystery of consciousness is real. Despite decades of neuroscience, we still do not know how subjective awareness arises from neural activity. Brain scans can reveal where thoughts occur, but not how it feels to think them. The hard problem, as David Chalmers described, continues to haunt modern science, hinting that our current models may be missing a deeper layer of reality. one that could eventually require a radical paradigm shift. In this sense, quantum consciousness serves an important role, even if it turns out to be wrong. It expands the conversation, forcing science to confront its own boundaries and to consider that consciousness may not fit neatly within the existing framework of physical law. It invites us to explore bold questions about the nature of observation, the unity of reality, and the role of awareness in the unfolding of the cosmos. Whether or not the Orch-OR theory or other quantum models prove correct, their courage lies in attempting to bridge two of humanity's greatest frontiers, the inner world of experience and the outer world of physics. Perhaps, in the end, the truth will not lie entirely with either camp. Consciousness may indeed have quantum aspects, but not in the way we currently imagine. Or perhaps it will turn out to be an emergent property of complexity, a classical process so intricate that it merely appears mysterious. Either way, the search for understanding consciousness is as much a philosophical journey as a scientific one. It forces us to question who we are, what reality is, and whether the boundary between the observer and the observed truly exists at all. In weighing both sides, one thing becomes clear: the mystery of consciousness endures. Quantum theories of mind, while unproven, have reignited a sense of wonder, reminding us that science and spirituality are not enemies, but partners in the quest to understand existence. Perhaps the beauty of the quantum consciousness hypothesis lies not in its certainty, but in its possibility. The daring suggestion that awareness and the universe are inseparable, two expressions of one grand mystery still unfolding. And that mystery brings us to the final reflection in this exploration, a moment of quiet wonder. After all the theories, experiments, and debates, what remains is a simple truth that transcends science. Consciousness, whatever its origin, is the most immediate and miraculous fact of existence. It is through consciousness that the universe comes to know itself. Perhaps the mind is not merely in the universe. Perhaps, in a deeper sense, the universe is in the mind. And so, after tracing this extraordinary journey, from the quantum dance of subatomic particles to the vast mystery of consciousness, we arrive at a breathtaking possibility: that reality itself may be conscious, that awareness is not confined within our skulls, but flows through the very fabric of existence. Perhaps the boundary between mind and universe is not a line at all, but a reflection, two sides of the same infinite mirror. Think about this for a moment. Everything you have ever known, every color you've seen, every sound you've heard, every joy and sorrow you've felt, all of it has unfolded within the theater of your awareness. You have never experienced the universe out there directly. What you call reality has always been an experience within consciousness. From that perspective, it's not that your mind is in the universe. It's that the universe is unfolding within your mind. Quantum physics has shown us that the observer and the observed are intimately connected, that the very act of perception helps shape what is real. Neuroscience has revealed that what we experience is not the world itself, but the brain's astonishing reconstruction of it. And philosophy reminds us that awareness, the silent witness behind all thought and perception, remains the one constant truth we can never doubt. You can question the world, you can question your beliefs, even your memories, but you cannot question the fact that you are aware. Awareness is the ground from which everything arises. So what if that awareness, your awareness, is not just personal, but cosmic? What if every conscious being, from a human to a bird to a bacterium, is a localized expression of a single universal consciousness, exploring itself through countless forms? In that sense, the universe might not be a cold expanse of matter, but a living tapestry of awareness, infinite, eternal, and self-reflective. Your thoughts, your emotions, your very existence, could be the cosmos thinking and feeling through you. And perhaps that is the deeper message of the quantum mind. Not simply a scientific theory, but a poetic truth whispered through the mathematics of the universe. That consciousness is the meeting point between the possible and the real. Every choice you make, every act of perception, every moment of awareness is a quantum event, a collapse of infinite potential into the miracle of now. This understanding invites humility and wonder. It suggests that behind the noise of thought and the boundaries of self, there is a vast stillness, the same silence from which galaxies spin and particles flicker into being. When you quiet the mind through meditation, reflection, or awe, perhaps you are tuning back into that original field, the unified consciousness from which all things emerge. So, as we close this exploration, take a breath and look around you. At the light falling on your hands, the air moving through your lungs, the sensations arising and fading in awareness. Everything you perceive, everything you feel, is consciousness dancing as form. And in that realization, the boundary between you and the universe dissolves. You are not a small fragment of creation looking out upon a vast cosmos. You are the cosmos, conscious of itself for a fleeting, miraculous moment. Maybe the mind isn't just in the universe. Maybe the universe is in the mind. And perhaps that is where the great mystery lies. In the space between knowing and wonder, science and spirit, question and silence. Because in that space, reality whispers its deepest truth, that we and the universe are not two things, but one infinite being, dreaming itself into existence again and again. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.